Well, welcome to Lecture 8 of the Introduction to Radar Systems course. This lecture will concern clutter rejection, MTI or moving target indicator techniques, and also pulse Doppler processing techniques. Now here's our old friend, the block diagram of the radar. And here's the Doppler processing section where we'll be discussing these MTI and Doppler processing techniques. And these techniques are used to suppress the effects of ground clutter, rain clutter, and other types of clutter that the radar will see as it transmits its beam out looking for targets of interest. Now here you can see we have a little bit of fun doing our coursework. Beside me in that photograph is Steve Weiner, one of my colleagues here at the laboratory, and Steve usually teaches, when we've taught the course with an ensemble of lecturers, Steve usually teaches the lecture on the radar equation, where there the issue is you're competing with noise and what you want is lots of power. When we do different lectures with different lecturers, I tend to teach the course on clutter and clutter suppression, and there finesse. You have to, finesse is the way to go. The signal processing techniques, it isn't just brute force power, it's finesse. So we use this as a little visual bit of humor to reinforce the two different ways that we maximize the signal in the presence of both noise and clutter. You might wonder what we're thinking while we're doing such stuff. Anyway, to move on. Here's that picture we showed you earlier in a little smaller version of a naval air defense scenario. And we've blown it up so it fills the entire screen, and we're going to use it just to point out the different kinds of clutter that we're going to be working on to reject and to see targets like this missile or this aircraft in the presence of. Rain clutter, ground clutter, man-made ground clutter like buildings or trees, mountains, detections from birds, also chaff too. Moving target indicator, MTI techniques, and pulse Doppler processing techniques use the Doppler effect to reject clutter. That's the fact that all of these different phenomena have some motion relative to the ground, pretty much always. And we're going to, or we're going to, in the case of ground clutter that doesn't have motion relative to the ground, we're going to notch out the clutter. But we're going to use filtering techniques that will break up velocity space so that we're able to see targets and filter away the targets, but actually filter away the clutter, but see the targets. And you can see from the thoughts, if you remember back, that ground clutter can be 10,000, 100,000 times larger than the targets of interest. If in the same range azimuth cell we have targets like aircraft and we have very heavy ground clutter, you're going to have to use a technique to see the targets in the presence of heavy clutter. Okay. First we're going to go, this is obviously an outline of what we're going to do. We're going to have an introductory section, then we're going to move through moving target indicator techniques, then pulse Doppler processing techniques, and then we'll summarize. Now on to the introduction. Generally speaking, MTI techniques, they just separate moving targets from the clutter. Okay? They use what I'd call high-pass filter techniques. They're techniques that reject low frequencies where the Doppler would be 0 or close to 0, like ground clutter, and they pass moving targets. They use just a couple of pulses to do this, 2 or 3 typically, and they use short waveforms, and they do not provide an estimate of the target's velocity. Contrasting that, pulse Doppler techniques separate the targets into different Doppler, into different velocity regimes. and the Doppler velocity regimes, Doppler frequency regimes. You're going to see shortly how they're related. In addition to canceling the ground clutter. So they tell you how fast the target's going, at least what its radial velocity is. They make a measurement of that along with getting rid of the clutter, suppressing the clutter. And they provide a pretty good estimate of the target's radial velocity. And that's the radial velocity is the velocity component along the line of sight between the radar and the target. In order to do this, they make much more complex filters than are used in MTI techniques. And to make these filters, you need more information, more pulses. They use longer waveforms, typically tens up to thousands of pulses to create the complex filter characteristics that will allow this good target measurement and rejection of the clutter at the same time. Okay. Now let's just look at the relationship between the Doppler frequency and the radial velocity of the targets. They're related through this equation that the Doppler frequency, that's the shift that's added to the base frequency of the radar. See, we're at a radar of 2800 megahertz, that's S-band, wavelength of about 10 centimeters. If a target was moving, there'd be an addition or a subtraction to the 2800 megahertz in the echo, depending on whether the target was moving towards you or away from you. And at S-band, according to this formula, the Doppler shift is about 1 kilohertz per 40 meters per second of radial velocity. Now, that's one data point, which is really the slope of a curve in Doppler frequency versus radial velocity. It's the one data point at S-band for each frequency, carrier frequency of the radar. There's a different relationship, different curve between Doppler frequency and radial velocity, and you can see they're linear. And I've plotted here 5 different radar bands: the VHF band, UHF, S-band, which is at 10 centimeters, X-band, which is at 3 centimeters, and a millimeter wave frequency. These pretty much cover the gamut from 150 megahertz to 35 gigahertz of most radars that are built. So you can see that, let's just look and see at a point on the curve. If we look up and at S-band, here we have the point we've taken at 3 gigahertz. We have a Doppler frequency shift of a kilohertz, and if we move down, let's see, 10, 20, 30, 40, 50. So it's 50 meters per second for exactly 3 gigahertz. And for 2800 megahertz, it'd shift down a little bit. Okay. Now next, let's go back and remind ourselves of what from the previous lecture, what the clutter spectra look like relative to aircraft. We see that we've got this big spike from land clutter that can be relatively relative to the noise level in an aircraft signal. It can be up 100,000 times higher than the noise level. And then we've got sea clutter and rain clutter and chaff and individual bird targets from individual birds or small flocks of birds. And then way up here, and notice that these are much lower. These next 4 sets of clutter are much lower in intensity than land clutter, and they go up to maybe 35 meters per second, 67 miles an hour, something like that, 70 miles, about that speed. And notice the aircraft are up here, their radial velocities might be 150 meters per second, going pretty darn fast. So what we'd like to do is to separate out one from the other. And this would be clutter that could potentially be all in the same range azimuth cell as the target. So we just can't use range, the echo delay time, or the angle, the pointing direction of the antenna to separate these out. These are saying, gee, we could have these clutter in the same range as this cell. And the characteristics are going to vary depending on what's in that cell. There might be some rain, and there might also be ground clutter present, or a mixture of any of them, or rain and sea clutter. Here we see that PPI display we showed you earlier, and in the center is the ground clutter. These are 5-mile range rings. And here's a big rain cloud. And you see it's a diffuse, it's wind-blown clutter. Okay? So it's this clutter that we're going to want to suppress so that we can see targets. Okay? Now actually I can point out here on this particular picture, right up there, if you blew this picture up high enough, you'd see a set of little lines. This picture isn't just one scan of the radar, but probably about 8 of them. And those 8 scans, we had an aircraft moving out radially in that direction, or in radially. And I'm willing to bet that's the echo of an aircraft target. And you can see if that aircraft target were here in the middle of the rain, without some kind of processing, you wouldn't have a chance of detecting it. Okay, now let's go over some definitions, because we're going to be processing data from pulses and the idea of pulse length, bandwidth, pulse repetition intervals. Let's go through those definitions, so later on when I use these terms you'll know what I mean. First, let's look at the diagram up above. We have here these little blue rectangles, and they correspond to the transmit pulses. And that you see we're sending out a whole set of transmit pulses in time. And the number we're sending out of pulses is M. The time between pulses is capital T sub r. Okay? And that T sub r is called the pulse repetition interval. It's the interval between pulses. Also associated with that is the frequency that the pulses are sent out, which is 1 over the time between them. We call that the PRF, or the pulse repetition frequency. That's usually measured in hertz, or kilohertz if there are 1,000 of them, that we're measuring. And here's the pulse, capital T is the pulse width, and the bandwidth of that pulse is 1 over T. And the duty factor or duty cycle of the pulse waveform that we're sending out is just capital T over T sub r. The pulse width over the time between pulses, and it's the fraction of the time the transmitter is turned on average. Now what we call the time of this whole interval, the M pulses times the time between pulses, is the coherent processing interval, or CPI. A lot of acronyms I'm giving you. And notice, remember, M is that number of pulses, and it's 2, 3, sometimes 4 for an MTI, or moving target indicator processing, and M's usually much greater for pulse Doppler processing. Okay, now that we've got these definitions under our belt, we'll reinforce them with this example, which sets the stage so you can understand what pulses and how we're processing the data, both with Doppler processing, with MTI processing. We have the echoes coming in an analog fashion. They have this voltages going up and down, and they go in after they come through the receiver. They go through an analog to digital converter, where we sample them one at a time. We just grab it. It's, so to speak, metaphorically, think we grab the pulse, see how big it is, and we store digitally what the digital number is of how big that is. And what we do is we take the data, both since the echo coming back, it is really a vector. It's got amplitude and phase. It's an electromagnetic wave vector that's got amplitude and phase. We have to characterize that by 2 numbers. And the way we characterize it, much like you would say, forces a vector, you measure it along the x-axis and the y-axis, say, if it's a two-dimensional vector, you know. So there's the x and the y-axis. And we characterize that by a real and an imaginary part. Not that that part is really non-existent. It's part that's at right angles in phase to it. And we call those the in-phase and the quadrature components of the complex number, which makes up that complex envelope of the received waveform. So this is actually two sets of A to D outputs. These complex I and Q samples then go in, and we, so to speak, we fill a memory. Let's look upstairs now at what's going on physically. We send a pulse out, and we listen and sample, listen and sample, listen and sample later. And for each of these times after the pulse went out, we wait in time, and each one of these corresponds to a greater delay after the pulse was transmitted, and if we get an echo back from the target, it corresponds to a further range. And that range is the speed of light times that echo time divided by 2. So these times correspond to a range. So we're going to fill up from this first pulse. At each of these little dots correspond to a sample time, and in this case right here, that's the 12th sample, we'll say, and it corresponds to a range, for example, of 8.3 kilometers. So we'll count over, and for this first pulse, we fill up this matrix with the real, and we have another matrix just like it we're filling up with the imaginary samples. And we fill up the real samples, and if you go over the 12th column, the number that's stored there is the echo, or the noise, if there wasn't a target there, from the 12th sample, which corresponds to a range of 8.3 kilometers. And then we also are doing that for the quadrature sample, so we have, in fact, another matrix just like this, which mirrors it, one for the in-phase and one for the quadrature component. And so we fill up all the different L samples till we're all the way back down to here. Then we transmit another pulse, and we do the same thing at the second row. And when we get down to the 12th sample, we'll be putting in the echo return for the range of 8.3 kilometers. So you can see that we're going to do that m times for each of these, for these m pulses. So we're going to have a whole bunch of returns, both real and imaginary, for that range cell of 8.3 kilometers. Okay? Now I'm going to steal a little bit of my thunder ahead of time. Now if we're dealing with MTI processing, we're just going to have this M will just be 2, 3, or maybe 4. So it won't be that tall a matrix that we're filling up, or memory I should say. This matrix is just a visualization of the memory in the computer, and it will be a number of cells long for each of the number of range cells that the radar has, going from the minimum range the target can see up to the maximum range until we send out this next pulse. Okay? Now let's move on to MTI techniques. We'll be going back to the same matrix or memory, that visualization, when we talk about pulse Doppler techniques. Now let's look and see how we take that stored data and we apply it to moving target, using moving target indicator techniques to reject ground clutter. Okay. Now, MTI indicator processing, with that, what we do is we notch out the clutter spectrum. Remember I said it's a high-pass filter. it provides a broad Doppler passband everywhere else. Now, at times 1 over the sample time, we have blind speeds occur. And they occur at multiples of the pulse repetition rate. And they occur when the sample frequency, the PRF, equals the multiple of the Doppler frequency. So if we have the Doppler frequency of whatever we're interested in at the cell we're interested in a certain Doppler frequency, if that's a multiple of the PRF, then we're in trouble. Excuse me. When the okay? Yeah. Okay, that's right. Okay. Now let's look and see how the simplest 2-pulse MTI canceller works and what it means. Let's consider we have fixed clutter echoes. And if you think out there in space, you've got a mountain. It's just out there. It's not moving. Big rocks. Think of a big chimney from a power station. And you send a pulse out, it'll reflect off that big chimney or power station. It's fixed. There's no Doppler shift. Send out another pulse. The clutter is fixed. And the 2 pulses that come back will be, there won't be a Doppler shift. There'll be the echoes will be exactly the same except for the noise. And if you just subtract one from the other, you'll get 0 except for the noise that was in the receiver. So you should be able to get rid of fixed clutter that's not moving at all. And it will be canceled if you just subtract 2 pulses. Now moving targets, on the other hand, will, since there's a change in amplitude from one pulse to the next because of their Doppler frequency shift, there will be a residue. And if one pulse is subtracted from the other, the result will be that uncanceled residue. Now let's look at that schematically first. Then we'll look over here at how one implements it. And here is an analog, the echo return from a radar. And you can see that here the echo is from the ith pulse. We could call that the 6th pulse and this the 7th pulse. If this is the 6th pulse, that's exactly the same, so that'll cancel out. But over here, the echo is a little bit different than right down here when we send a pulse out right afterwards. And that's because there's a target there that's moving, and there's a phase shift which causes the amplitude to be different. Likewise here, there's another target. And so what you'd see in the output of subtracting 2 successive pulses is a residue. And if you take the magnitude of the sampled residues for the different, these of course correspond to various ranges, you'd say there's a target here and a target here. Okay? And this type of display is called a radar A-scope because we're displaying amplitude as a function of time. How we implement that digitally is we just take the input data coming in and delay it just by the time between pulses, and then take the input data and subtract it from the delayed data, and then the output would give us this residue. And the output of a 2-pulse MTI is just subtracting 1 pulse from the previous pulse. Okay? Now, how do we evaluate how well an MTI circuit works? We do that with a quantity called the MTI improvement factor. And we've really got 4 quantities we're dealing with. The signal that we input, and the clutter that we input per pulse, and the signal that comes out at a given Doppler, and the clutter that comes out at a given Doppler or radio velocity. The MTI improvement factor is defined as the ratio of the signal to clutter that comes out to the signal to the clutter that comes in. And then that's evaluated at a given Doppler frequency. Okay? Now another way of expressing those terms is that the MTI improvement factor is the clutter in over the clutter out, and that's just how well we're able to attenuate the clutter, times the signal out over the signal in, and if we've processed the number of pulses, we'll get a signal gain. So it's the clutter attenuation times the signal gain, or the integration gain, evaluated at a given Doppler. Okay. Now the clutter you get out will depend on how you filter it, and that will be a function of Doppler, so you have to evaluate it at a given Doppler. Okay. And here we see that if we had it's a measure of how the filtering technique suppresses the clutter relative to the aircraft, and looks at how, first of all, this would be the input clutter and how the filter suppresses that, and then when you look at what the filter does to the aircraft. Do we have the filter that's adding a number of pulses and rejecting the clutter at the same time? Then there'll be some signal gain here, the target return would increase. So that's this definition, and you'll hear MTI improvement factor mentioned an awful lot later in the lectures, and it's just a measure of how well we do the clutter rejection and signal enhancement in this whole Doppler processing set of techniques. Now what I've just shown you is that definition of MTI improvement factor, and I want to plot for you what the MTI improvement factor is for a 2-pulse and a 3-pulse MTI canceller. First, let's just look at a 2-pulse MTI canceller. It's in red, and it's just subtracting adjacent pulses. And we see here its performance, where we're at S-band, and we have a clutter to noise ratio of 50 dB per pulse, and that's at a frequency. We have a PRF of 1,000 hertz. Now, here is the MTI improvement factor, and we see it's about 40 dB, a little over 40 dB, approximately. Okay. Now, if we take and we integrate 3 pulses, and a 3-pulse MTI is just taking the residue of 2 adjacent MTI, 2-pulse MTIs, and subtracting them. So if this were 3 minus 2, you get a residue. Then you take 2 minus 1, you get a residue. You subtract them. This is algebraically what that would be. And in blue we see the 3-pulse MTI. And these are calculations made with the ground clutter in here, and its spread is 1 meter per second, which is 10 hertz. And notice that the 3-pulse canceller provides a wider clutter notch and much greater clutter attenuation. You have much better MTI at attenuation of the clutter. Okay, now remember over here we see that we've got, if we had Doppler frequencies up here at 1,000 hertz, our target was at 1,000 hertz, it would be suppressed. And so how do we handle that? These points at 1 over the PRF in sample time, if the Doppler frequencies of 1,000 hertz, which would correspond to about 120 miles an hour, and 2,000 hertz, there's a multiplicity that happens because of the sample nature of the data. We wouldn't get good detection there. We have what's known as blind speeds. We'll talk about them later. And here you can see those blind speeds present for a fixed 2 kilohertz PRF at S-band. And you see the blind speeds at approximately here a little under about 90 meters per second, 180 meters per second. Now how do we deal with the fact that there are significant portions of Doppler space that we don't have good detection? One way of handling that is to stagger the PRFs. The staggering means to change the time between pulses, so that the time between the first two pulses would be 1 over 2 kilohertz. The time between the second pulse wouldn't be, as in this case it's 2 kilohertz, but 1 over 1.75 kilohertz. It'd be a little longer time. And when we do that, and we look at the signal-to-noise ratio relative to a single pulse, we get a gain that doesn't have blind speeds, except up here. We moved the blind speed up from about 90 meters per second to 640 meters per second. Okay? So you can get some increase in that Doppler visibility by staggering the PRF. But that has other problems, which I'm not going to get into, but at this time, such as it's hard to see targets. You can't subtract out targets that are beyond the blind, what's called the unambiguous range of the radar, and other such techniques. But in any case, staggering the PRFs is a technique that was used historically to get rid of those blind speeds. Now let's move on to Doppler processing techniques. But before we do that, we're going to take a break. Well, now it's time to resume Lecture 8. And this is Part 2 of Lecture 8, and the lecture is on Clutter Rejection, MTI, and Pulse Doppler Processing, and it's part of the Introduction to Radar Systems course. Well, now it's time to move on to Pulse Doppler Processing techniques. Here we're going to look at the whole concept of Pulse Doppler filtering, and we're going to go over some basic concepts to understand Pulse Doppler filtering in detail, and then we'll follow that with an example of the moving target detector, the so-called MTD implementation, and then we'll discuss range Doppler ambiguities, which will actually be in the third part of the lecture, and airborne radar, and summarize. But first, let's talk about these subjects. You've seen in the previous part of the lecture this diagram, and it's the data collection diagram for Doppler processing. It shows you how data is collected when a number of pulses marked here in blue are transmitted, and here we see the little dots of the samples of the echoes that are received. And we see here, just to review it, we see the pulses and then the echoes from that pulse, another pulse transmitted and its echoes, so that from pulse 1, this would be up here sample 12 at say 8 kilometers, and for pulse 2, sample 12, pulse 3, sample 12, and those samples for a given pulse number, say pulse 1, all those samples would fill a row. Okay, and these points at pulse 1, 2, 3, 4 at a certain range would fill a column. And here would be the samples at the same range gate. Okay, and so the data that comes in from the radar receiver from these different pulses would first go through an A to D converter where it would be digitized. We'd sample both the real and the imaginary part of the signal, the in phase and quadrature, I and Q samples, and these samples, the complex envelope of the received waveform, we'd use to fill up this. We visually show it as a matrix, what would fill up a memory. So we fill up the memory row at a time, and then we process it one range cell at a time. And the question is, how do we process these different, where we have multiple returns from the same range cell to give us Doppler resolution of the radar? Remember when we were talking about MTI processing, we just send out 2 pulses and we'd subtract them, or 3 pulses and we'd take the first one minus twice the second plus the third one, and that would be a kind of filtering, a high-pass filter that would pass anything that was moving. Okay? Now we're going to look at much more complicated processing, where instead of just seeing if the target's moving, we're going to make an actual measurement of the target's velocity, radio velocity, that is. Now here we have those M pulses coming in from the memory for one range gate, and they are processed in parallel through different filters. And this whole box in processing we call a Doppler filter bank. So those returns from the M pulses, I'll just say 32 pulses, from the 32 pulses in one range gate will be multiplied, each of the returns, the complex returns, will be multiplied by a weight. And that set of weights has a certain set of Doppler characteristics, which is shown here in this little curve. This curve is the gain characteristics in Doppler space of the set of weights that are used in filter 1. Now, I'm not going to get into the theory of how we develop these set of weights. That's more advanced for this elementary course, but just take it sort of on faith that I can develop a series of weights which will give me a response in Doppler space that will pass certain Doppler velocities. The x-axis is Doppler velocity, the y-axis is the gain, or how well the filter passes those Doppler velocities. And so this filter will pass this set of Doppler velocities, and the next filter will pass another set moved over, and another set near the center of the Doppler domain, and way down to the bottom, another filter. This, of course, is a bunch of different filters in between that would pass the much higher Doppler frequencies, or Doppler velocities. Now, I want to point out that these curves are logarithmic. That is to say that if a target was over in this side, it would be suppressed not just by the linear amount that these look like, but by a lot, like 100 or 1,000 or 10,000 times, because this typically would be 1,000 or 10,000 times lower than this peak response. So it's not a linear shape that I'm plotting here, it's a logarithmic shape. And whereas a target was at this velocity, it had come whomping right on through. So if after a target went through filter 1 and it came out, you know that its Doppler velocity is in this regime, and you know that it's not. The other thing to point out is if there was some clutter, like rain clutter, as we're going to see in the past, and we talked a little bit about rain clutter in the clutter lecture, the rain clutter would be suppressed and you could see a target. I view these filters as speedometers for the targets. And whereas the MTI filter says, is the target moving? A set of Doppler filters like this say how fast it's moving. They make a direct measurement. So what we're doing in this process of generating the output of the linear filter is we're coherently integrating all the pulses in the coherent processing interval, and we're weighting the pulses differently, and those weights will give, in combination for that filter, will give preference to certain radio velocities to go out, to be output from the filter. And the set of Doppler filters covers the entire Doppler band. We use this Doppler processing to reject clutter, and we also use it to resolve targets with different velocity segments, so it allows for fine-grained target radio velocity estimation. Okay. Now, what I'm going to do now is to talk about an example called the Moving Target Detector, MTD. And this is a nice example to choose because it is used as an example in just about every modern radar textbook of a good Doppler processing system. It's in an unclassified radar. This system was developed for use and the FAA's air traffic control radars. It's gained use in most pulse Doppler processing used in most modern radars now, just about all of them. But we can easily talk in an open venue about this particular implementation. And I might add, it was developed here at Lincoln Laboratory in the mid-1970s. Now, an interesting thing to add, because many of you are learning about radar now, and I've talked about in the past, is why do you talk about MTI filtering at all? Why don't you just talk about this pulse Doppler processing? Well, because radars have very long lifetimes, and there are many radars out there that were built in earlier times before these pulse Doppler processing techniques were available. So for understanding radars that are out in the world today, MTI techniques are important to understand. Okay. The second thing is to contrast the two, is that this particular process, the moving target detector implementation of a signal processor to reject clutter, you couldn't have done it in the 50s and 60s because of the digital revolution hadn't really come about. It was only with the advent of the invention of integrated circuits. To a lot of people in college now, integrated circuit seems like a pencil. You know, I mean, it's just like, what do you mean, invention? But back in the 70s was when the thought was that you could implement a lot of signal processing techniques that you could never have done before, because there was an exponential growth in the power of what computers could do. Back in the 50s and 60s, the power that we had with transistors, it would have been way too costly and huge in volume to implement a moving target detector. Just an impossible task to implement it in a radar with the technology available. It was just about ready to be done in the early to mid-70s, and that's when it was done. Now that we've moved another whole generation later, and we speak of hundreds of gigaflops, the implementations of the complexity of signal processing is just far more available to be done. It's almost like saying signal processing is now, for most radars, is a very small fraction of the cost of the radar. So I'm going to show you this implementation and just compare it historically between what we could do, say, back in the 60s and then in the mid-70s, and you can just extrapolate now with Moore's law what we can do in the year 2008 and beyond. Now, back in the days of late 1960s, an MTI processor would be implemented, and you divide the radar coverage up into segments that would say, 22 degrees by 25 miles or something. And you'd either have just the normal video unprocessed without an MTI, you'd process that whole area, or you'd process it through an MTI process. And the adaptive thresholding would be on that whole area. It wouldn't be on a specific range azimuth cell, because you didn't have the power to do it, And it was a time also where we weren't really understanding that hardware and software in the algorithmic needed to get together in a solid systems engineering point and work together in an integrated fashion. And consequently, at those times, in many cases, the software people who would be doing the tracking would point to the hardware people in the signal processor and say it's their problem. They sent us these false alarms. And then the hardware people would say, it's the software people. They can't develop a tracker to handle reasonable amounts of false alarms. Well, this digital revolution allowed solutions so that you could very nicely integrate the problem and come to a very nice understanding. So what was implemented in this MTD, for every range azimuth cell, for every CPI, coherent processing interval and width by range cell, and there were a couple 100,000 of them in the coverage, a Doppler filter bank with 8 or more Doppler filters. And then also, there was also a clutter map, which broke the range azimuth coverage up into 300,000 cells. And a zero velocity filter would just measure with what's called a one-pole recursive filter. It would just build up and measure the ambient background in that very fine cell and store it in a clutter map. And then and this would be so that even if a target was flying tangentially to the radar, if in that cell there was just receiver noise, you could set an adaptive threshold that would see the target. Output of the Doppler filter bank would go into adaptive thresholding, and we're going to see, let's see, we looked in lecture 5 at the different adaptive thresholding techniques, and an adaptive thresholding technique, just about like what we went over in lecture 5, was implemented for every range azimuth Doppler cell. So this system was adaptively thresholding every scan of the radar 3.5 million cells. And then there was post-adaptive thresholding to get rid of stuff that leaked through. And this was in software. Targets, since this was a low PRF radar, and you'll see what we mean by that in a later lecture, the range measurement was unambiguously measured, but the Doppler measurement was ambiguously measured. And so within a beam width, there were 2 different coherent processing intervals, and they were transmitted with different PRFs, or pulse repetition frequency. The radial velocity of the ambiguous targets would move around in the Doppler filter bank and give the targets a chance to compete with noise, and even though it was raining in at least one of those 2 PRFs. And then also birds and ground traffic were rejected through the post-processing thresholding, and a second fine-grained clutter map. Here is the picture of the airport surveillance radar. This particular one is located in Boston. It looks pretty sure that looks like the Boston skyline to me, so this would be the ASR-9 at Logan Airport. And here's a picture of the overlapping filters in the ASR-9. After the MTD was tested as a prototype at Burlington, Vermont, its characteristics were put into the specifications for the FAA's ASR-9 procurement, and the MTD was implemented in the ASR-9. And over here we see an example of how the ASR-9 could detect targets in the presence of rain. Here we see the response, and again notice it's a logarithmic. The gain of the filter is logarithmic. We see the gain of one filter, and we have a target in the center of that filter. And here we see the target with a radial velocity of 30 knots. And of course that means if we've got as you'll see when we discuss 2 view graphs later, that this could be a target with a radial velocity, a true radial velocity of 30 knots, or one with a velocity of 130 knots that, because of the so-called blind speeds, which we'll discuss 2 view graphs later, alias down or folded over and appears in this filter. So the target is right here. And then we have rain echoes, which, well, the rain echoes seem to be coming from 60 to 100 knots. Well, it turns out this is minus 20 knots, folds down in this visualization of the radial velocity, folds down into plus 80. And you'll see an example when we talk about blind speeds, this and ambiguous velocity measurements, these folding over effects. So that in this case, we have the aircraft competing at the peak, of this Doppler filter, and the rain echo being suppressed by the 40 dB down side lobes of the Doppler filter. So the rain echo would be suppressed, and the target would be seen in this particular filter. Okay. Now, what does this mean when you put it all together? Now, remember I showed you in the lecture on clutter this very heavy rain that was in Atlantic City, and here the the rain was just disgusting. It was 30 dB above receiver noise level. And it was the heaviest rain all summer in August of '75. And that was the day we chose to send up a Piper Cherokee and fly through that rain. And here we see the 40 scans of data that come out of the automatic tracker, radar only, not reinforced with a beacon or anything. And we see unity blip scan ratio of that Piper Cherokee as it's flying around in this very heavy rain. So we're suppressing the rain and we're seeing the target like a piece of cake. There are a few false alarms and a few misdetections. We can see right here a misdetection, and right there's a misdetection. And we see there's a road leaving the radar, and here are some detections from cars on the road. But pretty much the detection is really quite good. And in fact, it was revolutionary for the time in 1975. And over here we see a spectrum of the rain. And in this case, you see that the rain is offset. And if we took this spectrum and we displayed it not going from minus 60 knots to plus 60 knots, but from 0 to 120 knots, this rain would fold over up here, so it would appear as though the rain had a high radial velocity. That has to do with the ambiguity in Doppler velocity measurements that you have in these low PRF radars, these airport surveillance radars. Okay, now let's talk about Doppler ambiguities. And what that means is that targets can be moving at multiples of the PRF and appear to have the same radial velocity. Now, say for instance we have, and we look at a target that's giving a constant return, and we're plotting it in time divided by the PRF. Okay, and we sample at once every PRF. So say the radar was transmitting pulses at a kilohertz, and order of magnitude for an SBN radar that's 100 miles an hour. Now, if the target had no radial velocity, we sampled it, we get a constant returns. And that says, gee, target isn't moving. We can't measure any Doppler frequency from this. It appears to have zero frequency. So it appears to have zero frequency if we sample it and it's constant, or zero velocity. Now, say for instance that the target is moving at the unambiguous velocity, where the unambiguous velocity is the velocity that corresponds to the PRF, and we sample it once a pulse length, that once a time between pulse, we still get a constant value. So it appears as though a target that's moving at this unambiguous velocity, which is lambda times the PRF divided by 2, isn't moving at all, or at 3 times the unambiguous velocity. So the Doppler pulse waveform samples targets with the sampling rate equal to the PRF. That sampling causes aliasing at multiple PRFs. That means that there'll be a folding down, that a target moving at the unambiguous velocity appears like 0. 3 times the unambiguous velocity appears like it's not moving at all. What it also means that if the target were moving, say, at half the unambiguous velocity, or 1.5 times the unambiguous velocity, or 2.5 times the unambiguous velocity, you can't tell which it is because of the fold over, the aliasing. So 2 targets with Doppler velocities separated by an integer multiple of the PRF are undistinguishable. And so that what you have to do to see things unambiguously is tricks, which we're going to tell you about a little bit later, or you have to raise the PRF so that you can see things unambiguously in velocity. Sometimes that's not possible, and that leads to complexity in the development of the radar. So the equation we're going to leave you with is we've got a constraint on things. This unambiguous velocity, the velocity from 0 to this velocity that you can measure the velocity unambiguously, is the wavelength of the radar times the pulse repetition frequency divided by 2. Now let's look at range ambiguities. And let's take two targets. One, a distance r from the radar. Another one, a smaller target, a distance r2. And it's smaller probably, in this case, because of the r to the fourth factor. The sensitivity of the echo coming back drops off as 1 over r to the fourth. But its range is that range plus a range that we're going to call the unambiguous range of the radar. And the unambiguous range of the radar is just the round-trip echo time between the two pulses. And capital T sub r, which is 1 over the PRF, is that time between the pulses you transmit. So the unambiguous range is C times the time between pulses divided by 2. Now, range ambiguities occur when the echoes from one pulse are not all received before the next pulse. So let's look down here. We've got pulses we're sending out. If we sent a pulse out here, and we sent no other pulses out, we get an echo back at this range from this target. There'd be that delay. And we get a delay, much longer delay time from the smaller target 2. But if we send out another pulse sooner than the echo that this pulse generates from the one before it, then we can't tell when we listen after the second pulse whether the echo is from a target at R1, a target at distance R1 away, or R1 plus the unambiguous range. And so after we send out the second pulse, send out one pulse, then we send a second one out, you'll get both R1 and R2 coming back at the same time. And what that means is close targets, like clutter, say this was clutter, can mask weak, far-away targets that we want to see. And that gives a problem. So we have an ambiguity problem in range. So we've had a discussion of the unambiguous range and the unambiguous Doppler velocity. And as you might have noticed in the preceding two view graphs, these two equations, which describe algebraically what the unambiguous velocity is and the unambiguous range, each depend on the PRF, and one of them depends on the wavelength of the radar. So what we can do is for each frequency band of radars that we talk about, and here we picked a particular frequency within each of the bands, the major bands. And there are other bands too. I haven't put L band in here at 1.35 or C band, which is halfway between 3 and 10 gigahertz. But for each of these different frequencies that radars operate at and have a corresponding wavelength of the electromagnetic radiation, there is a connection between the unambiguous range you can have and the unambiguous velocity that you have. And that's defined by this line. Okay? Now, let's look at two different examples and see what this says. And before I do the examples, I'll say this one graph says you can't have your cake and eat it too in most cases. Now, You can't unambiguously measure targets out to arbitrary range and arbitrary radial velocity with one set of pulses. And we'll get to, in later pieces of the lecture, how you do that unraveling of the ambiguities to actually measure the velocity. But let's look now at these first two things. First, let's look at an air traffic control radar and say we want an unambiguous range of a little below 150 kilometers, and that corresponds to a PRF of about 1,000. If we build the radar at 3 gigahertz, that means we're going to have the order of 250 meters per second of unambiguous velocity, which is about 100 miles an hour. But aircraft that fly around terminal areas go a lot faster than that. So the measurements that you make with an individual coherent processing interval of worth of processing with one PRF sent out are going to be, can be made to be unambiguous in range, but they'll be ambiguous in velocity. Okay? And as I alluded to earlier, for each beam width, 2 sets of PRFs are sent out, and I'm going to show you later how we, with 2 sets of different PRFs, varying by 10 or 15%, you can unravel the ambiguity in Doppler. We'll show how we do that a little later. Now let's take another example. Say we have an airborne radar that's in the nose of a 747. It's used to see aircraft and weather and things that are up ahead of it. It wants to see, say 50 miles, 100 kilometers. And so it wants an unambiguous range of, say, we'll just pick this number up here. Well, when we go down to 10, also this radar wants to be able to see other planes that are coming towards it. And so it wants a reasonable beam width, and since the beam width is lambda over the aperture, when you only have an aperture of 3 feet to get reasonable beam width, you've got to go to high frequencies. You've got to make that lambda very small. And say we just pick 10 gigahertz, where you are 3 centimeters. That means at X band and this order of distance, you're going to have a very, very low ambiguous velocity, like 30 kilometers per second. Now say we make the unambiguous velocity we can see very high, 1,000 kilometers per second. That means the unambiguous range is going to be very small. So that means you can't have your cake and eat it too. And these radars tend to operate here where both are ambiguous, or one, so these ambiguities come into play, and you have to deal with them. That's the message that I want to leave you with.